In this video, we are going to do example 2 from lesson 15. We're asked to verify that the function satisfies the two hypotheses of the mean value theorem, and then verify the conclusion by finding the numbers C that satisfy the conclusion of the mean value theorem. The first hypothesis of the mean value theorem is say that the function is continuous on the closed interval, the second differentiable on the open. All right, so this function all the functions that we're familiar with are continuous on their domain. And the only domain restriction here is that x cannot be equal to 0, and 0 does not live in between 1 and 3. So since this function is continuous everywhere but 0, it's fine to say that this function is continuous on 1, 3. If you wanted to specify the domain of the function, maybe just for fun practice, everywhere but 0. So minus infinity up to 0, 0 to infinity. Another way you can write that is everywhere but 0, just for fun. It's continuous on its domain, which is a bigger set than 1, 3. So f is continuous on 1, 3. 2, f is differentiable on the open interval 1 is less than x, which is less than 3. And why is that the case? Let's go ahead and take the derivative. Before I take the derivative of this function, I want to write x plus 1 over x. I'm going to write 1 over x as x to the minus 1 power. Going term by term, the derivative of x is 1, plus the derivative of x to the minus 1 is minus 1, x to the minus 2. The derivative of this function is 1 minus 1 over x squared. Again, the only domain restriction, the derivative function exists everywhere except at x equals 0, and oh, by the way, 0 is not in 1 to 3. Right, so this function's derivative exists everywhere but 0, so it exists on 1 to 3. Okay, so those are the two hypotheses of the mean value theorem. Now we need to draw the conclusion. So by 1 and 2, the mean value theorem says that there exists, I'm going to do the backwards E for there exists, an x value, x equals c, in that open interval 1, 3, such that what's true? The derivative at that x value is equal to that slope of that secant line. F of b, in this case, if you want to label these a and b, you can. B is 3 and a is 1. So f of 3 minus f of 1 all over 3 minus 1. Right? F of 3. Maybe we'll do this. Color is always helpful. Okay, so what we want to do is we want to go ahead and find f of 3, f of 1, calculate the slope of the secant line. We know what the derivative is. We're going to set the derivative equal to this number and solve for the c that makes that a true statement, and we'll verify that that c lives, and maybe there's more than one, but verify that there's at least one c in between 1 and 3. All right, so I just rewrote the function just for ease on the scrolling. f of 3 is 3 plus 1 over 3. 3 is 9/3 plus 1/3 is 10/3. And f of 1 is 1 plus 1 over 1, which is 1 plus 1, which is 2. So let's go ahead and calculate this average rate of change, calculate the slope of that secant line. F of 3, 10/3 minus f of 1, 2, all over 3 minus 1. 10/3 minus 2 is 10/3, 2 is 6/3. And then we're going to divide by 3 minus 1. We're going to divide by 2, which is multiplication by a half. What do we have here? We've got 4/3 times a half, which is 2/3, right? 4/3 times 1/2. There's a secret times 1 right there. It's 2/3. Beautiful, so I need that piece, right? And we need the derivative at c, and find the c such the derivative is equal to 2/3. So f prime of x was equal to 1 minus 1 over x squared. F prime of c, I'm just using c for a particular x value. You don't have to do this, but I think it's helpful when we're learning. That's the derivative at c. I want to find the c such that this is equal to 2/3. And say that there is at least one c that makes this a true statement, and that c lives strictly between 1 and 3. So let's go ahead and solve this equation. 1 minus 1 all over c squared is equal to 2/3. I'm going to subtract 1 from both sides. And we get 2/3 minus 1. 1 is 3/3. 2/3 minus 1/3. Or sorry, I said the answer. 2/3 minus 3/3 is minus 1/3. Multiply both sides by minus 1. And we can see, in fact, here, let's just go for it. We can see that c squared is equal to 3. All I'm doing is I'm multiplying both sides by minus 1. I'm multiplying both sides by c squared and both sides by 3 to clear those denominators. Take the square root of both sides, and we see that c is equal to plus or minus the square root of 3. Now, which one of those numbers lives between 1 and 3? It's clearly not minus the square root of 3. And the square root of 3 does live between 1 and 3. 1.7. All right, and so we are done. There's your answer. We're going to look at this graphically, but what we have just done is that we've verified that my function is continuous on the closed interval 1 to 3. It's differentiable on the open. That really just amounted to saying, hey, the function and its derivative exists on their domain, and it has no domain restrictions in the intervals, respectively, the closed and the open. And then the mean value theorem says there's got to be at least one x value, x equals c, between 1 and 3, such that the slope of the tangent line there is equal to the slope of the secant line there. And we are going to look at this on Desmos. So I went ahead and calculated the slope of the secant line first, right there. Set the derivative equal to that number and solved for c and picked the c value that lived between 1 and 3. Let's now bring it over to Desmos, right? Here is our function, x plus 1 over x. I've set my a's and b's to 1 and 3. And here I am scrolling over my c. And when the slope of the tangent line is parallel to the slope of the secant line, we've found the c value that is the conclusion of the mean value theorem. So here I can see c is about 1.72, and that is the square root of 3 is what it is exactly, and you can see it's about 1.72. I have a little tolerance on here to have it change to green when we're kind of close to them being parallel, right? So that concludes our video for example 2.